All right. So chapter 9 is all about three-dimensional geometry. So we're going to start by just introducing a bunch of definitions as to like what the names are for some figures. A lot of this should be review or should be stuff we're already kind of familiar with. So let's take a look at these 4 pictures I've drawn here in 3 dimensions. So one on the far left is a, what do we call this thing? Cube. And this one, that's our rectangular solid. In the overseas in Europe, I think they call that a cuboid. Fancy, huh? What's this thing? Yeah, it's a pyramid, but we should be specific because the base of the pyramid can be different. So this one would be a square-based pyramid. And this last one is a, yeah, that's the triangular prism. So notice for a prism, the definition there is the faces other than the base of the figure are rectangles. So like the bottom and then the 2 sides of the ramp are rectangles. The bases of the figure, the things that are parallel to one another, are triangles. That's why it's a triangular prism. In general, we can talk about any kind of prism as just being some 3-dimensional shape where the 2 congruent ends and then the cross section have the same shape and area along the entire length of the solid. So whether these bases are like squares or pentagons or like icosahedrons or some, convoluted polygon, as long as they're parallel to one another and the thing is like uniform cross section all the way through, we just call that thing a prism, regardless of how many sides the thing has or how many sides the base has. Everybody's okay with that? Okay, next group of pictures. So the object there on the far left is a cylinder. This guy here, yeah, rectangular prism, right? Either is fine. What's this? It's the same thing except it's tilting, right? If the figure is not at a right angle, like if the height of the figure isn't perpendicular to the base, we call that an oblique rectangular whatever, or an oblique figure. So this is an oblique rectangular prism. Here we have that same triangular prism and just standing on the base instead of laying like a wedge. And then this guy we call a pentagonal prism because, again, the base is a pentagon. 4 of those 5 figures we'd classify as right figures. 1 of them we would not. We call them right if the height of the figure is perpendicular to the base. So the only figure there that's not right is the one that's leaning, is the oblique. Everybody's okay with that? What does it mean if we have like a pyramid to be that's right? What would that mean? Well, it's still the same definition. We need that the height of the figure is perpendicular to the base. But remember, the height of a pyramid is like an internal segment. So we'd be looking at something that's perpendicular to the base, like inside the figure. Let's see, what other 3-dimensional figures we got here? What about, we have these 4. So the one on the left is a sphere, and then this one that's half a sphere is a hemisphere, and then we have cylinder, which we've already mentioned, and this guy over here is a cone. So hopefully from geometry, we remember the area formulas for some of these common bases. So just to refresh some of those, since calculating the area of the base is going to be necessary for calculating surface areas or for calculating a volume, let's just kind of refresh those. So we have area of a triangle is 1/2 base times height, or we know from, was it last semester, the area could also be 1/2 AB sine C, right? Or was that this semester? I don't remember. When did we do the triangles stuff? Was it this semester? Yeah, I think it must have been. I don't know, it all fades together. Oh, yeah. Was it the first thing we did this semester? Okay. To calculate the area of a parallelogram, that's just base times height. Remember that a parallelogram also includes rectangles and squares and rhombuses, or rhombi. Is it? I don't know how you. What's the plural for rhombus? Grammarians. Anybody with an insight there? No, nobody really cares that much. It's probably not that important. We all know what we're saying. Another common area formula would be that for a trapezoid. So the area for a trapezoid is 1/2 the length of the one base plus the length of the other base times the height. And remember, we can identify the bases of a trapezoid really easily because those are the two sides that are parallel to one another. Another set of, again, these common formulas would be the circumference for a circle. Well, that's 2 pi r, or just pi d. Either is fine, where r is the radius and d would be the diameter. The area for a circle is pi r squared. And then the area for the curved surface of a cone is pi r L, where L is like the slant height. So if this is our cone, we're talking about the area of the curved part is not the base, right? So it's like all of that part. So R is here, and L would be like the segment BC. That's what we call the slant height. So if you build like a triangle internal to the cone, the hypotenuse of that triangle is what we call the slant height. And when I draw my letter L's when I do stuff like this, I use the cursive L because a lowercase l looks a lot like a number 1. In math class, that's a problem because I have 1s and L's be running around in the same thing, and that would confuse me. Okay. So if I want some other common stuff that we would have done in geometry, so like volume of a cone is 1/3 pi r squared h, where r is the radius of the base, the circular base, and h is that height. In the case of our picture, that'd be like segment BD. So if I want, let's see, another thing, the area, oh boy, what just happened there? That's not what I wanted it to go. The area of the curved surface for a cylinder is 2 pi r h. What do you notice about 2 pi r? Yeah, that's the circumference of the base for the cylinder, which would make sense, right? If you talk about the sides of the cylinder, if you kind of like cut off the bases and cut straight down and unfolded that, that's going to be a rectangle. One side of that rectangle is the height of the cylinder, and the other side is the circumference of the circle because it had to wrap around the base, right? What do we got here? So if we want the volume, another, again, more common geometry, volume of a cylinder is pi r squared h. The surface area for a sphere was 4 pi r squared. The volume for a sphere was 4/3 pi r cubed. In general, what are you noticing for these volume formulas? Well, I mean, these ones, yes, that's true. Yeah, it's like the area of the base times the height. And now it might need a correction factor if it's like a concave figure, like a cone isn't, like there's space missing kind of from that. But that's the gist of what's going on. So kind of continuing on, if I want the volume for a pyramid, that's going to be 1/3 area A H, and again that cap A is going to be area of the base. So if our pyramid is a square, it would be like side squared is A. If the area is like a regular pentagon, well, that's not quite as easy, right? I think you guys do areas of regular figures, though, in geometry class, and we'll circle back to that a little bit later. So the volume for a rectangular solid, like a box, we all know is length times width times height. And in general, for any prism, the volume is area of the base times the height, whether that prism is rectangular or triangular or pentagonal or whatever. Does all this stuff kind of ring a bell? Remember doing most of these things in geometry is the hope. Okay. I'm going to switch over to a PowerPoint now for the next sections because they involve quite a lot of drawing, and, well, it's a little bit easier to do it this way. I'll post these PowerPoints in the My Notre Dame sometime today so you can look at them. Everybody's ready to go? Do some PowerPointing. I love it. Is this one? Yeah, there it is. Okay. So section 2 is about the lengths within the three-dimensional solid. So when we want to find the length of a line within a three-dimensional solid, the goal here would be to build out a calculation triangle. So it's like a triangle that's embedded within our three-dimensional figure. What kind of triangle would be the optimal type of triangle to be making? A right triangle, where it's easy to use the Pythagorean theorem or SOHCAHTOA or a number of other tools at our disposal. Those are the best kind of calculation triangles. So for a right pyramid, we can draw this calculation triangle ABC. Everybody's okay with that? And that's kind of an obvious place, right? It looks like a right triangle in the drawing. There's no surprises there. That seems pretty obvious that I can do that. But Some of these have like some unexpected right triangles they don't look like right triangles on the paper, but you have to think about the thing in 3 dimensions, use your imagination a little bit, and then it's like, okay, yep, that is a right triangle. So for example, if we look at this cuboid here, the pink triangle here, triangle AED, is definitely a right triangle. The blue triangle here, FGD, doesn't look like a right triangle, but it is. How do I know that it is? Well, I know that the side FG is on the face at the top of the box, and the side GD is on the face on this side of the box, and I know those faces intersect at a right angle. So I know that angle G is a right angle. You have to look at it with a little bit of imagination, see it in 3 dimensions, because again, we're doing our best to draw a 3-dimensional object on a sheet of paper. So it takes a little bit of like imagination to see it, but once you've practiced that a little bit, they become pretty easy to see, but not if you're not looking for them, right? Okay. And again, so here are my 2 right triangles, where angle A is the right triangle in the pink one, and angle G is the right triangle, or the right angle in the blue one. Let's look at some other examples of like unexpected right triangles. Okay. So let's say we have a triangular prism. So again, the pink triangle, pretty obvious that that's a right triangle, where angle F is the right angle. The blue triangle doesn't really look like a right triangle though, because the perspective we had to draw this with, but it is. Which one is the right angle? Not G. B is the right angle. Good, because I know that like this edge has to be perpendicular to the base, because that edge is like a height. So I know angle B here inside the blue triangle is a right angle. Is everybody okay with that? Because angle GE is like on the interior. It's like through the middle of that prism. So that one shouldn't be a right angle. Okay. Again, we're just trying to build up some intuition because you have to do this yourself. So it's nice to like do a little bit of practice and see, okay, getting the hang of how to imagine these things, because it's not something that you do a lot of practice in geometry, right? Like visualizing something in 3 dimensions is not a super important geometry skill at a first-year geometry course level. Let's do another. So this pyramid here, we have the blue triangle, and no surprise, that's a right triangle. I mean, it looks like a right triangle there at angle F. The pink triangle is also a right triangle, though. Which one is the right angle? It's also F, because I know the height of the pyramid, the segment EF, has to be perpendicular to the base of my right pyramid. So angle F in the pink is also a right angle, even though it doesn't look like it when we draw it on our sheet of paper. Is everybody feeling okay about identifying these things? This tends to be the hardest part of this chapter, is just making sure that you can find the calculation triangle you need to do a problem. So let's go and do some examples now. So let's say we have a shoebox here. So it's a rectangular box. It's 32 centimeters long, 18 wide, and 11 high. And we want to calculate the length of the longest rod that will fit inside the box. So where is that? How are we going to arrange that rod to get the maximum length rod in there? Where is that rod going to be going? Yeah, so it's going to go from like the bottom back corner to the front top corner, right? That'll be the longest distance we can get in there. So we're going to start by sketching a picture of what we need. We're going to identify a calculation triangle. We'll redraw that triangle off to the side and then solve the piece off of that right triangle that we need. So here's our box. AG, that's going from the front bottom corner to the top back corner, is going to be our longest rod. So our calculation triangle is going to be ACG. Which one of those is a right angle? C. Everybody's happy with that? So I'm going to go ahead and redraw. Now, hold on a second. If I look at ACG, I only know one thing about that triangle, correct? I only know that CG is 11, and I don't know angles, right? And I know angle C is a right angle. But I know to solve that right triangle, I need another side length or another angle measure. Typically, which one's going to be easier to get out of a situation like this? The side length, because we don't know any angles anywhere, right? Everybody agree with that? So if I could solve for AG using another right triangle, I would just have used that other right triangle. So we're going to be looking for a way to find the side AC. Do you see a reference triangle where we know two sides that includes AC? How about ACD right here? Everybody see that one? And again, I know that's a right angle at angle D because the base is a rectangle, right? So I can solve for AC using that triangle. How would I solve for that? Pythagorean theorem. So I get the square root of 1348 when I do that. Now I have enough to solve for that triangle ACG. So 36.7 was just the decimal approximation for that square root of 1348. Yeah, 1348. So now I can do the Pythagorean theorem again to solve for AG. And I get square root of 1469, or about 38.33. So the takeaway from this, we have a problem when we go in and try to solve it, and the reference triangle we're building doesn't have all the information we need. Probably just means you need to build a second reference triangle that you can get one of the missing pieces, right? Yeah.
Where did you get 36.7 from?
That's just the square root of 1348 as a decimal.
Oh.
With what I was using, it was easier to make it a decimal than as a square root. You're good with that?
Yeah.
Okay. I said it, but it was fast, and you're probably writing other stuff, and I know it's hard to write and listen at the same time. I have the same problem. Talking and writing is also a problem, where you start writing what you're saying rather than what you mean to be writing. Yeah, these are teacher problems, though. All right, let's do another example. So here we have a square-based pyramid EABCD, where the sides of the base are 12 and the height of the pyramid is 9.5. We're going to calculate the length of EC. So that's like the tip of the pyramid down to one of the corners. And then we're going to have some point M that's marked halfway along the side of one of the bases. It's a midpoint for one of the sides of the base. And then we're going to calculate the length for EM. And then we'll ask to think about why those are not the same length. Okay, so we start by drawing a picture. So here's my picture. I've drawn in or labeled the height of the pyramid and the side length for my square. And I've included my pink reference triangle here. That includes the side EC. And then one of the sides that I know about. What's the problem though? I need two things inside of a right triangle to be able to solve this. Right? I need another side length or another angle measure. So I either need EC. Well, if I could get EC, I would have just done that directly because that's what we're asking for. So I need to either find FC or get an angle inside of this pink triangle. I'm going to go for FC because I don't have any angles anywhere. So I'm going to need another reference triangle that's going to involve FC. Yeah, so if I do ACD, that involves FC. What is the relationship to FC and AC, though?
Oh, that makes sense.
No, you're fine. What's the relationship between those? FC's got to be half.
Oh, so do it.
Mm-hmm.
Oh.
Yep, that's what we're going to do. Now, why is that got to be half? If this is a right pyramid, F is at like the very center of that figure. Everybody's okay with that? If this wasn't a right figure, then all bets are off, but it is, so we're good. So I'm going to use triangle ADC. So there they are. Notice I labeled F as like a midpoint there on it. So to find AC, I do the Pythagorean theorem and get the square root of 288. And I know that FC is half of AC, so I have 1/2 the square root of 288 for FC. Oops. Oh boy. Okay. So now I have enough to do the triangle EFC. I know EF is 9.5, and I know FC is 1/2 of the square root of 288. So when I do that, I get the square root of 162 1/4, which is about 12.7 for EC. We okay with that? So again, I just needed two reference triangles to kind of make that work, but that's okay. Part B asks to calculate the length for EM. So the reference triangle I'm going to use here is EFM. Do I have enough information to solve for EM now directly? I know EF is 9.5. Do I know what FM is? Yep, FM is 6. Again, if F is at the exact center, then the line here from M to the midpoint on the other side through F is going to be 12 also. So you got it. And then we can just Pythagorean theorem it up. And we get 11.24. Notice that EM is shorter than EC, right? EC was 12.74. EM is 11.24. How come those are different lengths? What? Sure. Can we use a more geometric explanation? Well, here's the easy explanation. They're both the hypotenusa of different triangles, right? The triangle EM or EFM that EM is the hypotenuse of is not the same triangle as the triangle EFC that EC was the hypotenuse of. Those are not congruent triangles, right? The two side lengths were different for the legs in each of those two triangles, correct? Everybody agree with that? Furthermore, what I think is also an excellent explanation is if I look at the triangle EMC, that's a right triangle, where EC is the hypotenuse and EM is a leg. You can't have a right triangle where the leg has the same length as the hypotenuse. That's bonkers. That would also be a perfectly reasonable geometric argument. You guys okay with that? So here, we visualize this, and we can see that, like, yeah, these are just like, they're the hypotenuse of two different triangles. We call EC a slant edge. And then EM is like the vertical height of the triangle EDC, right? Let's do another. So here we have some cone where the slant height for the cone is 11.3, and the angle at the apex of the cone is 53 degrees. And we're asked to calculate the radius for the cone. I've drawn in my reference triangle for us. Do we have enough information to do this? Yes, okay. So I see that 11.3 would be the same as the hypotenuse over here, right? Do we have BD or do we have one of these other angles? We okay.
You have the right angle and then you have the ABC.
Okay, so how does ABC get me the angle DBC? It's cut in half. Great. Why? Because it looks like it. We should be able to do better than that. It's not just because it's a height. The height will not automatically bisect an angle. What kind of triangle is ABC? Isosceles. Excellent. We know that the perpendicular bisector of the base is also an angle bisector for the apex in an isosceles triangle. That was a theorem that you would have done in geometry. Now, that's a pretty obscure one, and it's okay if you didn't remember. But the key here, the thing to remember, is that you only get the special angle bisector of a height if it's an isosceles triangle. If you don't have an isosceles triangle, that does not work. So the angle bisector won't be perpendicular to the base, and the perpendicular bisector of the base will not be an angle bisector unless your triangle is isosceles. So we can say this. How are we going to solve for the side DC then? SOHCAHTOA, great. Oops. Which one do I need? Yeah, so I say sine 26.5 equals opposite over a hypotenuse, and solve for R, and I get 504. What do you guys think? Okay. So takeaway here, what mode should our calculator be in this chapter? Degree, whole chapter in degree mode, okay? So if you haven't checked your calculator angle mode, take a minute, make sure it's in degree mode. And this feels like a good place to stop to me. So we'll stop here. For the homework set, we should be able to do like up through 7 for sure. But you can also do like lots of parts of these future ones. You probably just can't do like all of these angle pieces because that's the next section is finding angles inside of the three-dimensional figures. But rest assured, if you're clever, you've certainly done enough to where like finding the angle inside of this is not going to be that big of a challenge for you. It's the same idea. So if you wanted to work ahead past that, that's okay. But I think through 7 is probably all that we have lectured up to. Hannah? Of course. And let's just spend the rest of our time here getting caught up on homeworks, whether you're still doing chapter 8 stuff that you need to work on, or you're ready to start on your chapter 9 stuff to get a jump on that, or if you have chapter 8 questions for me that you want to talk to me about individually, all that's fine. But I think that's enough for today.